this lesson is going to cover Chapter 1, Section 2, which is measuring and constructing segments. First thing we're going to do is talk about something that you have an understanding of, is a number line. So what happens is we can identify a coordinate, which is a number that corresponds to a point on a number line. So what happens is we can give every single point, if we use some sort of measure, some unit of measure, some tool like a number line or a coordinate plane or whatever, what we can do is we can set our intervals up. In this case, notice that each interval's, let's say, going to be one space, right? And then we can assign a point to a particular value. So we could say, for example, that -2 is going to be identified by point A. -1 is identified by point B. And we can label it. And so this way we'll have 1 point per value, okay? And the benefit to this is, yesterday we discussed all about points and stuff, and points are kind of like just in space or whatever, but once we assign it to a particular number line, for example, we can now start to identify things about points like the distance between 2 points, right? So obviously you can easily identify the distance between point A, let's say, and point D here, simply by saying, well, if I'm going to travel from A to D, how many units will I need to travel? And notice each interval is 1 unit. So 1, 2, 3, 4. I will go 4 units to get from A to D. I'll also go 4 units if I travel from D to A, right? It doesn't matter if I'm going in one direction or the other, right? Distance is always positive. I'm just either going to the left or right, let's say, but it's still a positive distance. Now, mathematically, I can also calculate the distance between A and D. And what I would do is I would subtract one from the other. So let's say I go the distance from A to D. I'm going to do point A is at -2, and I'm going to subtract where point D is at 2. So -2 minus 2, and I'm going to take the absolute value of that difference. So the difference is -4, and the absolute value of -4 is 4. So notice that I can mathematically figure out the distance from A to D by doing subtraction. I can also do it the other way. It doesn't matter which one I put first. I could have said, well, 2 minus -2, and taken the absolute value of that. That's going to be the absolute value of 2 plus 2, or 4, which is also 4. So whether I count or I use the subtraction, the difference of coordinates formula, either one is going to give me the true distance between 2 points. And again, remember, you're never going to have a negative distance. So we're going to talk about some definitions here, and one definition that's critical is a postulate definition. What exactly is a postulate? You're going to be using these the entire time that you're in geometry. And we're going to use postulates as reasons for things or explanations of things. And you might say, another thing we're going to use is theorems. So you might say, well, what is a postulate? What is a theorem, right? Well, we'll get to theorems tomorrow. But a postulate is a statement that is accepted without proof. It's a fact. It's a true statement. It is a fact. But it is so obvious that we don't need to actually prove it. So when something is so obvious that it doesn't require proof of it being true, we call it a postulate. So the first postulate that we're going to talk about is the ruler postulate. Now, you're going to notice that all of our postulates and all of our theorems in this book are going to have a number associated with them. Well, that's not a number that's like the number of that postulate across the board. How postulates and theorems are named is based on the chapter in which they come or the order in which they are in your book. So even though in our book, ruler postulate is the first postulate that we're going to talk about, in another book, it might be the 10th postulate they talk about, and they might call it postulate 10. So the reason I'm telling you is I don't want you to worry about what this number is, okay? I don't care if it's postulate 1 or 15. What we want to know is what is it and what does it mean, okay? So this is the ruler postulate, and the ruler postulate basically tells you that the points on a line can be matched 1-to-1 with real numbers. So yes, you can take any point on a line and you can match it with a real value, okay? And once a coordinate system has been chosen in this way, the distance between 2 points equals the absolute value of the difference of their coordinates. And so that's what we learned in that last slide, okay? Construction, well, a construction is a geometric drawing that uses a limited set of tools, usually a compass and a straight edge. And so this is where we would ask you, let's say, to construct a line segment, construct an angle, construct a right angle, construct an angle bisector. There's so many things that we can ask you to construct. Now, we in this class are not going to be constructing angles. Just, I want you to know what it means to construct something, but we're not going to be constructing them ourselves. The concept of congruent is something that is a little bit confusing. When two or more things really, objects, for example, are congruent, it means that they have the same exact size and the same exact shape. There's a symbol that represents congruent. It's the equal sign, but it has this little squiggly part on top of it. So this is the congruence symbol. So let's say I were to take a box here, here's a square, and I were to copy it and paste it, right? We know, let's say this is square A and square B. I copy and pasted it. We know that these are exactly identical. So I would say that, square A is congruent to square B, okay? And congruent is a little bit different than equals, because what happens is because I'm not dealing with the same exact shape, I'm dealing with a completely different shape. It's not equal because it's not the same. It's congruent because it's a totally separate thing that happens to be the same. And so congruence is when we're referring to two separate objects, and that's why it's in the definition, okay? And when I say that it's the same, I mean it's the same. Like, I mean that if this side here is 4 units long, this one is 4. If this is 4, this one's 4. If this is 5, this one's 5. If this is 5, this is 5. And the angles are going to be the same. So whatever this angle is, this one matches it exactly. So the shapes have to have the same sides, the same segment lengths, the same angle measures, the same everything. I could completely replace one for the other and you wouldn't know the difference, okay? Congruent line segments, well, those are going to be 2 or more line segments that have the exact same length, okay? So now we're going to get to postulate 2, which is going to talk about segment addition postulate. Sometimes when you're writing this in a proof, instead of writing it all out, we'll say SAP, okay? You can, do whatever shortcut you want, but basically what the segment addition postulate tells you is if you have point B and it is between A and C, then the distance, right, between A and B plus B and C is going to be equal to A and C. And so let's think about that. Let's draw this out. If I happen to have here point A and I have point C and B is somewhere in between it. Now notice it says it's in between. It doesn't say it's in the middle. So a lot of times we always want to center things, but let's just write it here. Let's do it off center. Unless they tell me it's the middle, I'm going to do it always off center. And what it's telling me is that notice that the entire segment goes from A to C. Well, if I take the pieces, I've got piece AB, and then I have piece BC. And what this is saying is that whatever AB measures, let's say 2, and BC, let's say it measures 6, we know that 2 plus 6 is going to equal the whole thing, which would be 8, okay, or something like that. So what we're saying is all the parts of a segment add up to the entire segment. And that makes sense, okay? We also know that if the parts happen to equal the total, then this point here, this shared point here, has to be somewhere in between the two ends. And that's just kind of like reasoning or common sense. So the segment addition postulate in sum just tells you that the sum of the parts equals the whole when it comes to a segment. So now they're asking us, hey, plot these 4 points in a coordinate plane and determine whether segment JK and segment LM are congruent. Okay, so let's see. Let's go and let's do JK. J is located at negative 3, 4. That's here. K is located at positive 2, 4. That's here. So here's segment JK. And then segment LM starts at 1, 3 here and goes to 1, negative 2 here. So this is L and this is M. And so they want to know if those two segments are congruent. Well, we know if they're congruent, they have the same length. We could always come in here and just count. I know that J to K is 1, 2, 3, 4, 5 units apart. And LM is 1, 2, 3, 4, 5 units apart. So guess what? They're both 5 units long. So yes, they are congruent. JK is congruent to LM. Easy. Now, I could also do it mathematically. When I'm trying to find the length of JK, I see that J is 3, 4 and K is 2, 4. Well, notice there's no change in the 4, so I know that this is going to be a horizontal line. Where what changed was the X. So I can identify my length by doing the absolute value of the difference of the lengths. And I know that that equals 5. And I would do the same thing for LM. L is 1, 3. M is 1, negative 2. Again, notice that my X's didn't change, so I know that being that my Y's changed, I know that this is a vertical line. And I know that I can find the distance, again, by subtracting my Y's. And so I get absolute value of 5, which is 5. And again, notice I can prove it mathematically, or I can simply count. These sometimes always and nevers can sometimes be a problem. So you definitely want to take your time when you're looking at these, and you want to make sure that you analyze and think about any possible exceptions to the rule before you answer this. So it says here, the length of a segment is sometimes, always, or never negative. Well, this is definitely a never situation. You can never have a negative distance, okay? So even if you think about like a football game, you know, if you go forward, it's a gain of 5 yards. If you go back 5 yards, it's a loss of 5 yards. But it's not, you didn't travel negative 5 yards. You just went 5 yards in the opposite or incorrect direction, right? So it's going to be never negative. Here it says, if point S is between R and V, then S, sometimes, always, or never, lies on line segment RV. And again, if you're in doubt, draw it. Here's RV, and S is between it. So does it lie on the line? Yes, of course it lies on the line. So it will always lie on RV. A coordinate can sometimes, always, or never be paired with a point on a number line. Well, this is, again, an always scenario. Again, this was our ruler Whoops, I spelled ruler wrong. That's why I don't teach English, folks. That is our ruler postulate, okay? And yes, it tells you that you can always match a point to a coordinate on some number line or a coordinate plane or whatever tool we choose to use. And now in this last example, we're going to show you how we incorporate algebra and mathematics into geometry, right? So again, the first sentence sets up the problem for us. It says that point J is between points I and K. So I'm going to draw a number line. Here's I, here's K, and I'm going to put point J somewhere here in between. I'm not going to put it in the center just because I don't want to get in the habit of doing that. I only want to put things in the middle when I know they're in the middle. So I have here, it says, the next sentence says that IJ equals 2x. So this segment from here to here, this red segment, is 2x. JK, which is the green segment here, that equals 4x minus 6. And then the last thing tells me that IK, from here all the way to there, equals 30 units. So we need to figure out how can we use what we know about algebra, what we know about equations, what we know about segments to figure out these three values they're looking for. Well, the segment addition postulate that we talked about, right, the SAP, that one tells us that the sum of the pieces, in other words, 2x, right, plus 4x minus 6 has to equal 30, because it tells us that the parts add up to the whole. And so basically now you realize, well, when I set this up like this, I've got an equation. I can now combine my like terms, and I can solve for x. I can add 6 to both sides, and I can divide both sides by 6 to get x equals 6. So I had enough information to figure out what x was, because again, I knew the postulate that told me that the sum of the parts equals the whole. So now that I know that x is 6, well, then it's really easy for me to figure out the pieces. I know that ij equals 2 times x, so 2 times 6 equals 12. So ij is 12 units long. And then jk, I know, is 4x minus 6. So again, I'll substitute 6 in for x, and I'll get 24 minus 6, or 18. So if my math is correct and x does equal 6, I know that ij equals 12, and I know that jk equals 18. And if I add these up, I know that 12 plus 18 should equal 30, and it does. And so I know it checks out. So always check your answer at the end. Always make sure that it makes sense, okay? And always make sure that the answer you're putting is what they're asking you for. Because a lot of times people stop at x. You know, we might say, the original problem might say find ij, and you find x, you do all this work here to find x, and then you sort of stop and say, oh, it's 6. Where in reality, x is 6, but ij is 2 times x, or 2 times 6. So be very, very careful that you're answering what they're asking you to answer, okay? And that's it for today. So you're going to be doing the homework and then emailing me if you have any questions.